like that one. The same thing we did with the fire. So we took a domain which was 200 meters long, and we start making simulation varying the pressure boundary condition on both sides, and we record the mass flow rate through our domain. As you can see, the behavior of the fire within a tunnel is like an additional pressure loss the ventilation system has to fight against. So, depending on the fire size, we can get different curves. Obviously, the higher is the fire size, the higher is the pressure loss the ventilation system has to win. And in this case, for each fire scenario, we have two curves. The first one has been obtained with the temperature of the hot gas is equal to 800 degrees Celsius, and the dashed line is obtained with temperature equal to 1200 degrees. This range should be the error of our way of simulating the fire. So the real curve should be something in between. So once I get this curve, in my network model, if I have a branch where the fire is, I know that the behavior of this branch has to be like this one. So we took our tunnel and we look at the minimum ventilation requirement to achieve critical velocity within our tunnel. So first we did a CFD, just one-dimensional calculation, and we saw obviously with different fire size, and then we did the same calculation but adding the additional pressure losses we calculated using the CFD model. So what we saw is that the flow resistance and the buoyancy of the fire is not negligible at all, and in our case, with our ventilation system, the traditional one-dimensional model calculation underestimates the ventilation required for the worst case scenario by up to 40%. So in this work, we present a novel approach to calculate the ventilation condition within the tunnel. The model is able to maintain the coupling between the fire and the ventilation system, so we are able to see how the fire and the east sides affect the final ventilation condition within the tunnel with a given ventilation system. The model used two different scales to treat the fluid dynamic problem within the tunnel. One-dimensional scale in the region where the flow is behaving one-dimensionally, and CFD model when we want to represent the fluid behavior close to a disturbance. Obviously, as the computational time is really low, the new approach is well suited to conduct parametrical studies, and at the end, as you see, we applied our model to calculate the performance of the ventilation system for a model tunnel. Thanks. If you have any question, I'm here.
Thank you for your presentation. We have time, so questions, please. Anyone?
For the 1D analysis, how do you treat the widths of the tunnel? If you have larger widths, does it still behave as one-dimensional?
No, because we calculate the right diameter of the tunnel. So the bigger is the width of the tunnel, the bigger is the right diameter. So the lower are the pressure losses due to the friction. So yes, you can take into account this.
More questions? So I have one question. So you told us that you compared the 1D model with the 3D model. Could you please tell me if you try to get the experimental results and to see how?
Yeah, we did this for cold flow. We had some experimental measurement from one tunnel, and we used our approach to see if it was good to model the fan, for example, like in a periodic behavior. So we built the curve and we compared the one-dimensional result with additional information provided from the CFD with the experimental data. I have a slide here. So, and Here, this is the comparison. So was we were lucky, but the comparison between experimental data and numerical data is really good for a cold flow. We didn't have any data with hot flow within the tunnel.
Thank you.
I have a question. How do you make to unite both models? When you make the simulation, you are using a 3D model in, around the fire, and away from fire, you use a one-dimension model to make the calculations.
Yeah.
So how do you merge both results?
Okay, in this case, like during the computational time, both models they cannot exchange any information. What we did is to take first the CFD model to run this as many times as we can, and we reconstruct the behavior like in terms of pressure difference and average velocity. We reconstruct this behavior and then we put this behavior in the 1D model. So it's made like a posteriori. It's not that like at the same time 1D model and CFD model exchange information at the boundaries.
Then you are making like a shorter tunnel 3D calculation for the zone, and then you feed the one-dimensional model with this information?
Yes. We put like in the one-dimensional model like an additional pressure losses due to the fire in the region where the fire is.
Okay. Thank you very much.
Any more questions? If not, I would like to thank you very much for your presentation. Let's start. More questions? Sorry.
I think your example was applied to a road tunnel.
Yeah.
Right? And you have mentioned the difficulties in a road tunnel.
Yeah.
And I believe in railway tunnels, most of the difficulties you encounter in a road tunnel would not be effective. So, like the obstacles of the vehicles and so on.
Mm-hmm.
So, can we say that your approach is even more practical for railway tunnels?
Yeah, I think so.
Because it is more linear and your periodic domains will be almost identical.
Yeah. I think above all, the longer is the tunnel, the better is to try to simplify the calculation. Because otherwise we had to wait months to get any CFD data.
Very much. The next paper